Hi, I'm Ritika Ganguly, Principal Engineer and Architect in the Network and Edge Group of Intel. And I have Iris Ding, Service Mesh Architect in the Software and Advanced Technology Group of Intel. In this video, we will share how Intel delivers an open, secure, and accelerated service mesh, harnessing the underlying hardware capabilities. Istio and Envoy, widely used in cloud microservices, Edge SASE, CDN, and other edge deployments. Intel is one of the top contributors to Istio and Envoy communities, especially around performance enhancement, security, and network functions. We release quarterly and we align with the latest upstream version. Iris will now take you through one of the use cases.
Thank you, Maritika. So security and multi-TLS are key features for the Istio service mesh. So by default, the Istio control plane will acting as a certificate authority server for all the workload in the mesh. And each of the workload need to generate their own private keys and get the cert signed from the central Istio certificate authority server. In the edge side, the gateway need to handle the incoming traffic and do the TLS termination. All these three scenarios, the certificate authority server, the multi-TLS, and the gateway, are heavily relying on the private key to do the TLS handshake. So by default, the upstream Istio will store these private keys in clear text. So this picture just shows two samples in red box that it can easily grab the private keys for the certificate authority server and the multi-TLS. It also means the attackers can easily break the mesh communications. Hence, Intel Service Mesh provides a secured solution to guard the private keys, while Intel Software Guard Extension, or Intel SGX. It is available starting from the 3rd Gen Xeon processor. So Intel SGX provides a process-based trusted execution environment. The trusted part will be executed in the SGX enclave, which means it cannot be accessed by other software, and even for the privileged software like the operation systems or the BIOS. So in our case, all the private keys will be stored and executed in the SGX enclave. So now, using this solution, if you try to see the private key for the C certificate, you will get nothing. So this solution is also purely rely on the CPU itself. It doesn't need any additional hardware. Next, Maritika will take you through some acceleration architecture details.
Thanks, Iris. Typically, a service mesh will inject a sidecar proxy alongside your application to handle both inbound and outbound traffic. Due to this additional hop, service mesh provides traffic management, security control, observability, and QoS. However, this also brings performance penalty for workloads. Intel Service Mesh accelerates the data plane traffic by harnessing several Intel hardware capabilities, providing up to 70% performance benefit. Some of these acceleration solutions are available in the Intel Service Mesh as shown here in blue, and we'll cover some of those next. If you see the TLS handshake, it is a very CPU-intensive operation. A service mesh gateway will handle a lot of concurrent new connections, and TLS handshakes take a lot of CPU cycles. One solution for handshake acceleration is via Intel Quick Assist technology, or Intel QAT for short. Intel QAT is a hardware accelerator which is available starting from 4th generation Intel Xeon processor. In a Kubernetes environment, QAT device plugin will pass through QAT virtual functions to the workload pod. Envoy QAT private key provider implemented TLS private key method and delegate the sign and decrypt operation to QAT device asynchronously. This frees up CPU cycles and boosts overall performance. But TLS acceleration can be achieved through yet another method, right, Iris?
Yes, definitely. Another option for TLS handshake acceleration is via crypto multi-buffer. Crypto multi-buffer is based on AVX512 CPU instruction set, which is available starting from the 3rd Gen Intel Xeon processor, and they do not require any special hardware enabling. The multi-buffer instructions gather several RSA or ECDSA operations into a shared buffer. When the 8-slot buffer is full or when timer expires, the RSA operations are processed using the single instruction multiple data instructions, which provide greater throughput than processing the RSA operations separately. Crypto multi-buffer private key provider is an Envoy extension. When a new handshake happens, Boring SSL invokes the private key provider to request the cryptographic operation, and then the control returns to Envoy. Just running Envoy on a suitable platform and enabling the crypto multi-buffer private key provider in the Envoy configuration is enough. This is a summary for the TLS acceleration performance. As you can see, Intel QAT provides the best performance for both request per second and latency. Crypto multi-buffer improves the overall performance as well. Regular expression matching is utilized in Envoy for multiple places, such as filter matching, role-based access matching, and routing matching, etc. By default, upstream Envoy utilizes RE2 as the regular expression matching engine. It is low performance and the matching will take a longer time, especially if, for example, the routing rules have more entries. Hyperscan is a high-performance regular expression matching, which also based on AVX 512 as well. Hyperscan support has been delivered in Envoy as an official contrib since version 1.24. You can easily enable Hyperscan to replace RE2 for nearly every regular expression matching in Envoy, as it has been implemented as both an input matcher and a generic matcher in Envoy. This is a comparison between RE2 and Hyperscan. You can see Hyperscan can improve both latency and QPS. Do you know you can enhance load balancing of requests? Meritica will take you through that.
That's an excellent topic that we have worked on for almost 2 years. So Intel Dynamic Load Balancer, or DLB, is a hardware-managed system of queues and arbiters for connecting producers and consumer threads. It's available from 4th generation Intel Xeon processor. It is a PCI device in the server CPU, on core, and can interact with software running on cores. Now, what does it provide? It provides a lock-free multiple producer-consumer operation. The queue is implemented and managed by hardware to save CPU core and memory. What have we done with it in Envoy? Well, Envoy uses Linux kernel for scheduling incoming connections to different Envoy worker threads. The dispatch is purely based on connection 4-tuple hash and is unbalanced on the CPU cores. So some of the worker threads will be super busy, while other worker threads are idle. Envoy now supports, in addition to the exact connection balance, a balancing solution using Intel DLB. We can now dispatch client requests through the software locks, without the software locks, and save CPU cycles. If you see the performance comparison now between Envoy exact balance, kernel balance, and using DLB, you can see there is a throughput and latency benefit to a much larger extent. We have many other accelerations that we have implemented in Envoy. Next, Iris is going to show you a demo of QAT and TLS acceleration. If you are here at KubeCon 2023, come by the Intel booth to see all the demos in person. Otherwise, we have detailed white papers and user guides for each of them. Reference the previous section for links and details. Thank you for joining us.
This demo is about TLS acceleration via Intel QAT. So before that, we need to do some preparation and installation work. We first need to make sure the Intel QAT device plugin is installed and working now. Next, we will verify the QAT devices has been present in the Kubernetes worker node. So you can see here, the QAT device has already been present in the Kubernetes worker node. The next, we need to put the QAT device into the ingress gateway through the Istio operator. So in this deployment file, we have allocated the QAT resource to the ingress gateway port. We are using the Intel service mesh delivery, and also we need to enable the QAT private key provider here in the configuration file. So next, we will clean up the environment. We will install Istio from the beginning and wait for the installation finished. Now Istio has been installed. We will also install the FortiIO server, so it will serve as the workload, and we will send the request from the FortiIO client through the ingress gateway. So in this case, the ingress gateway is on the host fortio.com, and the port is 388778. So we are using FortiIO client to send load to running for 1 minute, and the connection is about 2000. So we will run it to see how it behaves in the ingress gateway after we enable the QAT acceleration. So after it has been running, the result will be saved in a CSV file. We will compare the result without the QAT acceleration. So now we will reinstall Istio from the beginning. You can see here, this time in the Istio operator file, no QAT device has been requested. We are still using the same Intel service mesh delivery here. So we install it again, and then we install the FortiIO server and the ingress gateway and configure it to route the request to the backend FortiIO server, and we ran the same FortiIO load test for 1 minute with the concurrent 2000, send to the same ingress gateway host. So now it also has finished running. Let's compare the result now. So without QAT, the average latency is about 0.6 millisecond. With QAT, the average latency is almost the half. It's about 0.3 millisecond. And the throughput without QAT is about 3,000. Now with QAT, it's almost double. It's around 5,000. That's all. Thank you.